Hello, everyone. Good morning, afternoon, and evening. Dear authors and invited guests, welcome to Technical Session 90. I'm Pranjal Banage, and this session would be moderated by me. On behalf of Global Knowledge Research Foundation and GR Scholastic, it is my great pleasure to welcome you to the 11th International Congress on Information and Communication Technology, ICICT 2026, in London, UK. The 11th edition of the conference is being organized in a hybrid mode. The physical event was held a day before yesterday in London, UK, and the virtual event is being held through Zoom from 25th to 27th February 2026. I hope you'll enjoy the knowledgeable and interactive sessions throughout the day. In this session, we have 6 presentations. Each presenter will be given 12 minutes for the presentations and 3 minutes for question and answers. In 10 minutes, I'll raise a gentle reminder. There's another request to all the participants that you all stay connected with us till the closing remarks. If you have any queries or updates, then you can write it to me or to my co host in the chat box. Before we start the session, I would like to introduce you all to the session chair of this session, Dr. Sachin Gupta. He is the Dean of Research and Innovation and Professor of Computer Science and Engineering at Maharaja Agrasen Institute of Technology, Delhi, with over 24 years of teaching and administrative experience. He is also associated with MethodAI.com, a leading edtech platform, as an AI product consultant. His research interests include wireless sensor networks, NoSQL, blockchain, and network security. I would like to invite Sir to give his opening remarks.
Thank you so much for having me. I'm looking at so many presenters there in the meeting. This is probably my 10th session with ICICT as a session chair, and I have enjoyed the deliberations immensely. They are raising the bar every year with the kind of papers that are being accepted to the conference. And I'm sure we have some brilliant researchers who will be publishing and presenting their work today. I'm looking forward to learning. Times are changing so much, so fast, so rapidly. And these conferences allow us to keep in touch with what is happening around the world. Thank you so much for having me. All the best to all presenters.
Thank you so much, sir. Moving forward, we'll start with the presentations. I'd like to apologize in advance if I mispronounce your name. So we'll start with our first presenter, Yaroslav Omelyanenko. I would like to invite him to present his paper on a time complexity study of parallel fitness evaluation for the NEAT algorithm. You may please present your PPT and start with your presentation.
Good morning, everyone. Thank you. Let me share my screen. Okay, do you see it?
Yes, sir, we can see your screen
clearly. Okay, thank you. So my name is Yaroslav Milyanenko. I'm affiliated with Institute of Software Systems of National Academy of Science of Ukraine. And I would like to present my work, a time complexity study of parallel fitness evaluation for the NEAT algorithm. First, I would like to start a few words about what is neuroevolution and NEAT algorithm as a part of this family of algorithms. Neuroevolution algorithms are widely used for solving optimization, control, and reinforcement learning problems. They have the following features which make them fit for this kind of tasks. So neuroevolution enables the use of evolutionary algorithms for training artificial neural networks. Neuroevolution seeks to algorithmically abstract the process of natural evolution, isolating the creative aspects for application in domains beyond biology. The primary abstraction adopted from natural evolution is the concept of organism biological fitness and its role in natural selection. Also, neuroevolution algorithm operates directly on the population of the solution solvers rather than on individual organism through the process. And as a result, we also have several advantages of the narrow evolutions that include the following, but not limited by them. Automatic identification of individual artificial neural networks components during the training. So it can be selected specific activation function or for different types of neurons, for example. Automatic determination of topology of produced neural network. And also it can be used to create some kind of meta learning. So it also can be create automatically even learning rules. One of the well-known algorithm in the family of neural evolution is the NEAT algorithm. It's neural evolution of augmenting topologies. And the most important feature of the NEAT algorithm, which defines its potential, it's the ability to gradually evolve the topology of artificial neural network during the learning process. So algorithm starts with the simplest solution, and during the process, it will complicate it until final solution is found. Thus, we go through all steps with minimal possible efforts. And primary objective of the NEAT algorithm is to reduce complexity of discovered network topology due to this. And this can be achieved by the way how it is implemented. So topology expansion through the gradual complexification, speciation, so we can isolate several groups of found solutions organism in order to avoid them to lose their properties acquired during the evolution. Mutation, it's introduced changes upon the end of each epoch of evolution. Innovation numbers, also known as historical markings, and crossover or genome recombination. So actually on the right we can see a few examples how mutation can be implemented. It's like adding new connection or adding new node. And at the end of each evolutionary epoch, we need to evaluate the fitness of population and the fitness of each individual algorithm. This is done usually by simulation of some kind of physical process. And this simulation often is quite computationally complex. So it will require a lot of time to be executed and a lot of resources computational resources to be spent. And after this evaluation is done, there would be selected champions among the population, and they will be used to produce the next generation of population. So actually on the picture we can see how two parent organisms can recombine and to create the child organism. And such approach has a significant impact on performance because we actually need to run this simulation for each organism in population for each epoch of evolution. And as a result, the dominant computational cost of the NEAT exactly arise from the fitness evaluation stage at the end of each epoch of evolution. So in general, we can represent this mathematically as a formula which includes number of organisms in populations, time spent for evaluation of each algorithm, time spent on mutation of found champions, and time spent on actual speciation. And in practice, this evaluation time dominates over all other parts of this equation. And also, because network complexity increases during evolution, we have increase of computational costs at each new stage of evolution, because not only a number of organisms can be bigger, also uh, each organism have more nodes or connections, which also bring some computational efforts. And we can formalize this complexity as a time complexity model. So actually it includes time on fitness computation, time on speciation, time on reproduction. So it can be represented further using standard big O or big theta notations. And moving further, we can come up with a practical formula which can be used to do actual calculation of the time spent for one generation of evolution based on each part of that formula. And also here I would like to introduce the concept of using parallel computations in order to have simulation performant in parallel threads. So, for example, we have pair worker nodes, and each node can do physics simulation for separate organism. And this can greatly reduce time spent on the at the end of each epoch for this fitness evaluation stage. And we introduce it here as a big pair. And also there is some constants, alpha, beta, gamma, which represent computational cost for speciation, reproduction, and activation weight computation per organism, which can be found empirically. And also because this is now become distributed parallel computation, we have some costs related to manage such a computation. We cannot have infinite number of parallel workers, because then we hit the wall with scheduling, management of interprocess communication, etc. And the last part of this formula actually give us this extremum and plateau below which we cannot achieve any further improvements. And there is a question how to find optimal number of workers. And we can use for this further mathematical simplifications and come up with this formula after some kind of differentiation, which give us P star, which is optimal evaluated number of workers. And after that, we would like to confirm our hypothesis and our formula with some kind of experiment. And for this was selected double pole balancing experiment, which is actually accepted benchmark that enables assessment of computational efficiency of evolutionary algorithms, sensitivity to parameter selection, and effectiveness of computational parallelization. After that, we have done several experiments for different number of population size and come up with the following graph. So actually on the graph we can see that in blue we have experimental data, and dot red it's approximation of our model analytical, and it come pretty close to the experimental data. And also because we have a plateau of the near the minimum, we cannot actually select, it does not make sense to select the exact minimum because, for example, we can allow themselves to have plus minus 5% for Pareto optimal zone where we accept our values. So actually it is drawn in this area. So it's like any number here, number of workers allow us to get good results. And also there is a graph which represent how population size, workers count, and time per specification can be represented as a 3D surface, and for each selected population size. And the main result of the work is like we can have some kind of calibrations work for smaller populations in order to estimate analytically the number of workers to be selected for the bigger population, which in order to reduce time for this run. And as a result, so we have presented formal time complexity model, identified fitness evaluation as a principal computational bottleneck, the analysis of 5% Pareto optimal region demonstrates that even in the presence of prediction errors, the optimal number of workers fit our analytical model, and also we confirmed that physical consistency of proposed time cost model and its ability to adequately capture changes in performance regions of parallel implementation of the NEAT algorithm. So that's it from my side. Thank you.
Thank you so much. The session chair, sir, do you have any questions for
Yes,
him?
sir. Uh, I just wanted to understand one thing. I mean, we are working with humanoids presently, and there is a lot of reinforcement learning where the computational complexity grows huge at times. So, pardon me if my understanding is not correct, but what I am getting from it is that we should be able to redesign an artificial neural network with lesser parallelism within the layers, that the number of neurons can be optimized using your method, and that would lead to lesser time for training. And am I correct if in my assumption?
Yeah. So actually, due to this algorithm, we can build optimal, cost-effective neural networks with optimal number of neurons, not like in deep learning where we just engineer it by giving huge numbers of neurons, but exactly select optimal configuration.
So this also brings us to some explainability in the network instead of that being a black box.
Yeah, and also in my another studies, I was looking for this, and we when we got really simple neural networks, it can be easily explained what not actually do what.
Absolutely delightful. Thank you so much for your presentation.
Thank you.
Thank you, Yaroslav, for that. Such an amazing presentation. Very well structured.
Thank you.
Yes. Now I would like to move forward with our next presenter. I would like to invite Sarbhagya Ratna Shakya to present his paper on lightweight vision-based violence detection models for edge device suitability, a comparative analysis. You may share your paper by sharing your screen.
Hi, good morning. Can you see my screen?
Yes, sir, we can see your screen.
Okay, thank you. Hi, good morning, everyone. So I'm Sarvagya Ratnasake. So today I'm going to present my paper on on evaluating lightweight vision-based policy detection models for our edge device suitability. So this is the comparative analysis of various lightweight models that we have over there. So along with me, Dr. Varela is also the co-author of this paper. So this is the presentation outline that I'm going to follow today. So we're going to look at the introduction and background of this research. Then I will talk about the data sets that we have used for the project, the methodology that we have follow for the whole experiments. Then I will provide some information about the experiments and then talk about the results. And then I will conclude with some discussion and conclusions over there. So when we talk about the video surveillance system, so it has been deployed in various for various domains, like in the security, in public monitoring, for analysis the activities of human in terms of the old age homes. So this continuous manual inspections of this video data is very impractical, as it is very time consuming and very resource computing over there. So recently with the development of the resources that we have, so we can use the real-time automated video analytic solutions that can be used in early detections of those abnormal, let's say the behavior of the human or the subject in the videos, for timely intervention and risk mitigations over there. So traditionally, some of the deep learning models like the CNN and the recurrent architectures that has been used to capture those complex spatial and those temporal activities of the persons from the videos. But with the development of the lightweight models that we have in recent years, so we can use those lightweight CNN models that has demonstrated those high recognition performance and can be applied in the resource constraint is based development, such as by simply using through the through surveillance camera, simply using our smartphones. So this is what we are looking at in this experiment over here. So for our experiment, for our evaluations, we use two publicly available data set. So one is the real life Boylan's data set. So this data set consists of 200 YouTube videos that are evenly split between Boylan and non-Boylan. So 1,000 of Boylan data set and 1,000 of non-Boylan, let's say, clips over there. This Boylan samples, so it consists of some of the Boylan behavior in diverse settings, in roads, in movies, in let's say the surveillance footage over there. Whereas for the non-violent videos, so those include some of the daily activities of the human, like let's say from the sports, walking, jogging, and those kind of activities over there. So this dataset has the clips that has the range of around 3 to 7 seconds and has varying spatial resolutions over there. The second one is the real world fight dataset. So this is also a balanced dataset. It also has 2000 videos. The difference between this and our previous dataset is this has the source from exclusively from our real world surveillance footage. So all of the clips are recorded through our surveillance video cameras. So which make it a little more challenging and realistic benchmark for our experiment over there. And all of the clips that we have on this dataset are 5 seconds long with variable resolutions. So while talking about the methodology that we have, let's say, followed for our experiments, for our data processing, after we extract the frames from the clips, so we resize those clips in the resolutions of 224 by 224 pixels. Then we use some of the data augmentation techniques, like for example, the horizontal flipping and the adjustment of the brightness over there. Then we use the standard mean and the standard deviations to normalize our frames that has been proposed on ImageNet. So for our experiment, we evaluate in two distinct frame sampling strategies, let's say the technique over there. One is the temporal frame averaging, where we extract 100 frames from our videos, and each of those 10 consecutive, let's say, segment are grouped from those 10 frames each. Then we compute a per pixel average of those 10 frames and then result the 100 aggregated frames that serves as the inputs to our models over there. So the reason for using this one is to include more temporal informations from our videos to the models over there. Second is the general uniform frame sampling technique, in which we extract 10 frames uniformly from our videos and use it as our input to our models over there. So we use 6 lightweight CNN architecture for our experiments. So these are used to to extract the special features from our inputs frames over there. All of our models, all of these 6 models are pre-trained on our ImageNet dataset. The sequence of these high dimensional features that we extract from these models are then sent as an input in our bidirectional LSTM model. The bidirectional LSTM model captures the temporal dependencies by processing the sequence in forward and the backward directions over there. So we perform our experiment using the Python. We use the NVIDIA Quad P5000 GPUs for our experiments. We train our models up to 10 epochs, whereas we use the early stopping methods with the presence of 10. We train our model using the Adam optimizers with a learning rate of 0.001 and the batch size of 10. So this is the comparison of the model size that we use for our lightweight CNN models. So MobileNet V3 has the approximately the smallest size, which is around 10 MB, as compared to our other models, whereas the SqueezeNet has the maximum of 680 MB over there. The total size of the models also shows that this can be implemented in the low resource, let's say low memory devices over in real, let's say, time. So this is the result that we got for our RLB dataset and our RWF dataset for our TFA temporal frame averaging methods. So we can see that on our table too. So it reports the performance of all models of our RLB dataset. Efficient net if the net shows the maximum accuracy of around 0.9558%, and the MobileNet V3 has the smallest, or let's say the lower average inference time. So this average inference time is the time it required to run its activities of, let's say, predict, classify its activities of our testing data over there. So it has the lowest average interface time of around 0.306397 over there. So when we look at the generalization performance over there, so it was more challenging. So the RWF dataset has more challenging over here. So the result for our RWF dataset is on our table 3. So as expected, all models experience a performance drop. So if we compare the result on table 3 with table 2, most all of the performance has been dropped over there. Whereas MobileNet V3, it emerged as the strongest overall performance with the accuracy of around 77% and the lowest average interference time of around 0.34 seconds over there. So while we look at the results on our RLB and our RWF dataset with our UFS uniform frame sampling technique, we see that the overall UFS have the improved performance as compared to our TFA. So MobileNet V2 has the maximum accuracy of around 97% over there, whereas the MobileNet V3 have uh, the MobileNet V3 small has the most efficient model with an average interference time of, no, sorry, the ResNet 18 has the most lowest interference time of around 0.27 second over here. So this shows, so from this experiment, what we can conclude over here is that the effectiveness of our temporal sampling strategies in our Boolean detection depends on both the dataset characteristics and the model architecture over there. So it does not show the exact let's say the output performance. On real life, RLB dataset and our uniform frame sampling consistently outperforms the temporal frame averaging across the architecture. So MobileNet V3 have consistent strong performance across the dataset and the sampling strategies with the lowest interference time and the compact size of around 10.05 MB over there. So if we compare the size and the performance, MobileNet V3 small shows the better performance, or let's say the more better performance and the better lowest resources or the memory that it required. So from this, we can see that the lightweight models such as this MobileNet V3 Small and the ShuffleNet V3 has the strong balance between the accuracy, speed, and the memory efficiency, which shows that this can be implemented on the low uh, resource device, or let's say the edge device over there. So evaluating this shows that it is suitable to implement this boilers detections on our resource constrained edge device over there. MobileNet V3 stands out as the most suitable model, achieving high accuracy and having the lowest memory size over there. And also, it shows that it has the fast interference. And also, uniform frame sampling is generally more robust than applying the temporal frame averaging over there. So, which can be competitive in more noisier footage for certain models. So these are some of the reference that of the models and the dataset that we have used. Uh, Thank you everyone for listening to my presentations. And if you have any questions, I will be happy to answer that one. Thank you.
Yeah. Nice presentation. Thank you so much. I think you should be able to implement it even in a Raspberry Pi Pico environment with the kind of
Uh,
uh,
yes, so some of the
that.
microcontrollers that we have that suppose the edge computing, so we can implement that one on those microcontrollers. Yes.
Okay. There is one thing, a piece of advice rather, that I saw through your tables. You were actually speaking about accuracy. When it
Mhm.
comes to videos like violence or any sensitive data set like that, we would usually test in for precision and recall both in addition. So
Yep.
accuracy is not the only parameter that you should be reporting, but your parameter values in the tables were equally good. So that is why I let it pass back then. But ideally, you should report it because this is
Yeah.
reasonably required in any simulation where you are working with the sensitive data like this.
Mhm. So we have included that on the paper, but due to time constraint over here, so I thought maybe the accuracy and the time interference is what we are going to discuss over here.
You would
Yep.
have to tell people that accuracy is less of a good metric here. It is actually precision
Yeah.
and recall are more important.
Yes. Yes. Yeah.
Right?
Thank you. Yes.
Yeah, thank you so much.
Thank you.
Thank you so much, sir, for that insightful and well presented talk. Now, moving forward, I'd like to invite our next participant, Abayomi Agbeyangi, to present his paper on Beyond the Metric, Digital Access Barriers and Perceived Resource Needs Among Learners in Underserved Schools. You may start with your paper by presenting your screen.
Good afternoon.
Good afternoon, sir.
Hi, good afternoon.
Yes. I'm Abagbayagi. My co-author is Dokosi. We are presenting a paper on digital literacy, which is titled Beyond yeah, a digital barriers and passive resource need among learners in underserved school, presenting from Walter Sisulu University in South Africa. So this is my presentation outline. Okay, the research is on digital literacy, and we try to see how we can measure learners' lived experience as per the digital literacy level in underserved schools. And we try to say that digital technologies are now essential for learning and even communication and even for future employment. But there are persistent digital exclusion from low resource schools, which we try to see how we can measure that. We are able to see and noted that many learners face poor internet connectivities, high data costs, and limited access to devices, and also inadequate digital skills. We are able to understand from the research that access alone does not guarantee meaningful digital participation. From the experience of the learners, we're able to understand this. And from the problem statement perspective, we're able to note that most of the literature focus more on the quantitative access metrics of digital literacy. And we also noted that measured device ownership or internet availability does not really show the various forms of digital device. And also some of the literature also overlooked learners' lived experience, which study tried to address by going using qualitative means. The research gap, we noted that limited qualitative understandings also include how learners experience digital exclusion and what are the resources they believe that are needed for learners, particularly in low resource environment. Our objective, we try to explore learners' lived experience, trying to see what they actually experience as per digital literacy, and also some key barriers to their digital access and the resources the learners perceived as necessary for them to be able to be digital literate. Also, how barriers and this need aligned within the underserved schools in and underserved communities. As theoretical frameworks, we try to use two theoretical frameworks, digital inequality frameworks and capability approach frameworks. We try to see how we can frame the study within this theoretical framework. Digital inequality framework talks about digital exclusion being multidimensional, which could include material access, skill, usage, and support, such that access most times does not equal to meaningful use. Capability approach focus on learners' ability to access into real opportunity based on their capability, such that digital inclusion could equal to expand freedom of use, not just about the devices. So we try to frame the study in these two theoretical frameworks, yes. Methodology, as I said, we use qualitative description design, and we three underserved secondary school was used within the Eastern Cape region of South Africa, which is one of the regions that are not quite well developed to the other regions. We 286 participants out of the 300 that were administered the questionnaire to, and we were able to go to get about 286 returned with valid responses on challenges, 241 and 222 resource need responses. We use reflective thematic analysis, whereby the actual writings from the learners deducting their responses within the team. Try to design that are equivalent to their responses. About female 59.8, female participant, just an overview of the participant. I think I can move. This examples of the question administers and their response. So within the team, we're able to identify 4 categories of barriers: connectivity and infrastructure constraints, device and data limitations, digital skill and support deficit, power and energy instability. So let's take each of them. Some of the learners' responses include no network or don't have network connectivity at my community is bad. And the impact of this is that it interrupts their learning, including having to do assignments, do research, and this resulted in unequal participation when compared to other learners in an urban, well-resourced environment. On device and data poverty, we see a lot of them not having laptops. Sometimes they run out data, which is and this forms kind of a division of device poverty, data poverty, and is this access is also unstable, and which is a kind of sustainability, because if they could not have access to devices, how would they be to be literate digitally? The other barrier we were able to infer from their responses also include digital skill, where learners respond as I do not know how to email sometimes on laptop, being on train will help, I need help on the computer. The key insight from this is that learners are not automatically digitally skilled, so it cannot be inferred that even though they have device, that can result into them being skilled. So access without skill oftentimes could result in unstable opportunity. Even though there's computer, learners might not be able to use that. The other barrier we are able to infer from the responses is power instability, which sometimes at the point when we are collecting this is profound, but even now, I think it has gone down tremendously. So learners respond that sometimes there might not be electricity, load shedding can also stop them from doing online work. The key insight is that reliability is also foundational for digital learning. As per the need mentioned by the learners, categorize this into devices, affordable and reliable internet, digital literacy training, human support system, and which devices could include laptops, smartphone, even though they mentioned that their parents does not have phone oftentimes, including laptops. Being able to afford the data connectivity, which is important for doing research or assignment online. Digital literacy training, which is also very, very important. They quite some learners even mentioned that their teachers were not well trained in digital skills. So as such, we're able to infer from our findings that digital exclusion is not just lack of devices or not just lack of internet. Digital precarity, even with some kind of layered condition involving economic constraint, having not being able to afford laptops, not being able to afford internet, not being able to afford power in their homes, electricity in their home, infrastructure stability, including power, skill deficit, which, even though some of them have said they have laptop, but they could not even send ordinary email. These are secondary school students. So we also were able to note some weak institutional support from this. As per recommendation for infrastructure, we recommend school Wi-Fi, rural broadband expansion, solar charging solution, which can take care of light, load shedding, and the rest. Affordability, there could be some sort of subsidy as per data, subscription, human capacity, teachers, being trained and retrained. Curriculum integration, this can also be incorporated, data skill can also be incorporated into various curriculums, such that education must shift from just provision into empowerment based on these recommendations as per human capacity development. So in conclusion, digital exclusion in underserved school, as we are able to in our research, multi-dimensional, which could include and such that true digital inclusion will require reliable infrastructure, affordable access, skill development, and supportive human networks. For future, we believe if could also include teacher digital in the responses, we'll be able to measure how the scale is also resulting in. Thank you very much for listening.
I thank you for your presentation. It resonates very much because I was conducting a program with Nigeria, and majority of the problems which you have mentioned, they are practically something that we face it during the program. So it's a very relevant matter. Yeah.
Actually, the study was conducted in some rural community in South Africa, not Nigeria.
Yeah. So we find that there is a lot of, in fact, people have digital devices.
It's a general challenge in Africa, general. Yes.
I found one specific case because we were teaching them AI and ICT, and the challenge was that ICT was a challenge itself. So bringing them to artificial intelligence was a even bigger challenge at times. Thank you for your presentation.
So that was part of the reason why we undertake this study. Thank you.
Thank you, sir, for such a wonderful presentation and the knowledge that you shared with us. Moving on, we'll have our next presenter. I'd like to call upon Richard Rocco Crenshaw to present his paper on post-based attention and multiple instance learning for pitch tipping detection. You may start your presentation by sharing your screen.
Right. Can you all see my slide deck?
Yes.
Hello? Yeah, okay, cool. All right. Hello, everyone. I'm Richard Rocco Crenshaw from the University of Alabama Brains Laboratory. Today, I will be presenting our work on pose-based attention and multiple instance learning for pitch tipping detection in baseball. So pitch tipping is when a pitcher unintentionally reveals a pitch type through subtle, repeatable cues in the delivery. Those cues can be tiny, but if they're consistent, they can create a real competitive advantage for the batter.
Hold on, Ricardo, just a minute.
Oops.
I'm looking at the screen and I am finding like the slides are. Can anybody else see the slides, please?
I don't think so. I think you haven't shared your screen yet.
Yeah, please.
Okay.
Yeah.
Yeah, that would do it. My bad. Sorry.
No worries.
Is this any better?
Yeah, there is it. A very beautiful presentation.
All right.
Thank you.
All right. Did the full screen go through?
Yeah. Go ahead.
All right. Okay. I guess I could just start from the top. Sorry about that. All right. Hi, everyone. I'm Richard Rocco Crenshaw from the University of Alabama Brains Laboratory. Today, I'll be presenting on our work on pose-based attention and multiple instance learning for pitch tipping detection. So pitch tipping in baseball is when a pitcher unintentionally reveals a pitch type through a subtle, repeatable cues in the delivery. These cues can be tiny, but if they're consistent, they can create a real competitive advantage for the batter. So our goal is to detect and localize these cues from standard TV broadcast video using weak supervision and to output something that's actually interpretable enough to support coaching review, not just a class label. So let me start with why broadcast tipping detection is a difficult problem. So There are three big constraints that really drove our methodology. First, the evidence is temporally sparse. The tell may show up for only a small fraction of the delivery, and we do not know where it is within the delivery ahead of time. Second, broadcast video is messy. The camera angle will change. The picture is sometimes occluded, and there are multiple people in frame, which makes pose estimation noisy and sometimes incomplete. Third, and this is really important, is that we really need interpretability. If the model predicts a pitch type, we also need to know like a reason that we can give to a pitching coach to actually inspect, like where in the motion did the model focus. So to kind of illustrate how noisy even pose extraction with modern models can be, I have a sample right here in this video, if you can see it. The pitcher's arm itself is just misestimating, and it's very noisy. So we need something that's robust to that. So with that in mind, we'll talk briefly about the data set and labeling setup. So we built a data set of 1,057 pitches from a single Division I collegiate pitcher across 16 games spanning 2 seasons. Each clip contains 3 seconds before the release, and we annotate the release frame so that the pre-release window is consistent. Pitch type labels come from True Media Metadata, which is a service that the governing body of collegiate sports pays for all teams. So the labels are true. We evaluate 2 label settings, a binary task, which is fastball versus non-fastball classification, and a 3-class task, which is fastball versus breaking versus off-speed. And I want to be clear about the scope. This is a single pitcher proof of concept. The goal is to test whether weekly supervised learning can localize discriminative cues in real broadcast footage and produce interpretable outputs. So this slide is a one slide summary of our entire method. So I'm going to walk through it left to right. We start over here with the raw broadcast footage, and we run YOLO V8 pose to extract a 2D skeleton sequence. So for like, if you have T frames, each frame has 17 joints and 2 coordinates, X, Y, within the image frame per joint. And because the broadcast frames include multiple people, we have to do pitcher isolation, and then we normalize the skeleton to try to reduce dependence on camera framing and zoom. Next, we split the full sequence into overlapping temporal windows. So each window is 8 frames with a stride of 4. So each pitch becomes this bag of overlapping windows. Each window is then encoded with 1 of 3 backbones, producing a 64-dimensional embedding per window. And then we use MIL attention pooling to weight the windows and produce a final pitch prediction. The attention weights here are what actually let us interpret which windows matter the most. That bag of windows idea is exactly why the multiple instance learning approach fits this problem. So in multiple instance learning, you don't label each individual instance, you label the bag, the entire thing. So here, the pitch is the bag and the windows are the instances. We know the pitch type label at the pitch level, but we don't know which moment in time during the delivery could potentially contain a discriminative cue. So attention-based multiple instance learning learns a weight for each window. In effect, the model learns that these windows carry more evidence for the pitch type prediction and these don't. So MIL solves that weak supervision issue without ever actually seeing any sort of timestamp annotation. And it simultaneously gives us this natural interpretability handle. Inside that MIL framework, we compared 3 different window encoders. And we kept everything else the same. So the MIL pooling and the actual head are the same, so we get a fair comparison. The first encoder that we tried was a grouped MLP baseline. We split the joints into 5 groups. So we split them into the head, throwing arm, the glove arm, the torso, and the legs, and we encode each group in fuse. It's very simple and fast. Second is a temporal transformer. It treats the frames as tokens and uses self-attention across the 8 frames per window to capture short-range dynamics. And third is a motion vert style skeleton transformer, where each joint time pair becomes a token that lets the model attend across joint in time directly. All 3 output the same 64-dimensional window embedding, and then the MIL pooling and classification head are identical, like I said. Now, we tested not only backbones, but we also tested which parts of the motion actually matter. We evaluated 4 temporal regions relative to release. So early, which is really early on in the delivery, mid, in the middle, late at the end, and then the full 3-second window. If you combine that with 3 backbones and 2 label modes, we get 24 configurations total. We ran 5 random seeds per configuration, reported mean, and standard deviation. So the idea with this sweep is that it can answer where in time the information actually is and which encoder captures it the best. So there are three real takeaways from this with the at least accuracy results, and we'll talk about all the other stuff later. But across models, the early window is consistently the weakest, as you can see here on the left. This suggests that, at least in this data set for this specific pitcher, the set position and the early movement don't reliably contain enough of a signal to separate pitch types. Second, performance improves in the mid and late windows. You can see it increasing, and is best when we use the full pre-release interval. So this implies that context matters, but there is useful evidence distributed across the entirety of the delivery. Third, the temporal transformer is the most consistent winner. In the best configuration, the transformer plus the full window, we get about 81.4% plus or minus 1.4 for binary, and 75.2% plus or minus 1.5 for the 3 class. So the takeaway from the slide is that the full context plus the temporal attention over frames is the best match that we found for the weakly supervised tipping detection. So now that we see that it works, at least predicting pitches, the next question is, where does the 3-class model struggle? So for these next 2 slides, we're going to focus just on the 3-class problem because it's more difficult and for the sake of brevity. So this table breaks down the 3-class performance into precision recall and F1. Fastball is the strongest class. Off-speed is also fairly strong, but braking is the most challenging. So the macro averages are all in the mid-70s, which is important because it reflects the performance across classes rather than just the majority class. So we're not just, only predicting fastball and getting it right the majority of the time. So in the next slide, we'll talk about a confusion matrix so you can see like the dominant error pattern directly. So the dominant confusion is between braking and fastball, which is illustrated by this structure right here. Off-speed is comparatively better separated. There are fewer confusions into fastball than we see for braking. And this makes intuitive sense because the mechanics of a braking pitch look very similar to a fastball pitch until very late in the delivery. And when you start adding in all the noise that you get from the pose from broadcast video and viewpoint variation, all that stuff, it makes sense that you might miss some of the subtle differences. So the most important interpretability question is the attention actually meaningful, or is it just a visualization? So this slide is our functional test for attention, and I think it's one of the most important validation pieces. The red bars correspond to mask top K. So we remove the windows that the model assigns the highest attention. When we do that, our accuracy drops substantially, especially as K increases. And this tells us that these windows actually contain predictive evidence. And the green bars correspond to keep top K. So here we throw away everything except the most attended windows, and accuracy stays relatively high once K is a few windows. This means that a relatively small subset of motion contains most of the discriminative signal. So taken together, this supports the claim that attention is genuinely localizing informative temporal evidence and not just producing a nice looking heat map. So once we trust attention as localization, we can use it to surface candidate tells that a coach can actually inspect. So for high confidence correct predictions, we take the top attended windows and compute simple kinematic descriptors. So things like stride length, trunk tilt, glove height, hip shoulder separation, to name a few. The goal is not to claim like causality here with the biomechanics. It's to show that the model's attention selected segments can produce human legible differences aligned with meaningful motion descriptors. So the idea is that this can easily become a workflow. The model points you to the time windows that matter, and then you can summarize what differs mechanically in those windows across pitch types, which is much closer to something a coach can actually use than just being able to predict the pitch. So the main takeaway is that attention-based MIL over pose windows works for broadcast pitch tipping discovery. It handles weak supervision and provides temporal localization that supports interpretability. Empirically, or as we can see with the evidence, performance depends strongly on temporal context. So the full pre-release context is the best, as well as the temporal transformer is the strongest and most stable backbone across all configurations. Our next steps are to evaluate group splits by game to try to test more as a robustness test to broadcast conditions, as well as scaling beyond a single pitcher and exploring multimodal fusion to try to improve fine-grained three-class discrimination. Longer term, we want to do expert and loop evaluation to help determine whether or not we're actually surfacing real tips. Thank you. I'm happy to take questions now.
No question there, but I am sure that you are going to make some team very, very lucky someday when you publish your results and they are going to have a very unfavorable advantage. Am I right? This is what
Yeah, I'm hoping. We're doing this in partnership with our collegiate baseball team. So we're about ready to actually start rolling out because the season just started. And so I'm hoping that we'll do well this season.
yeah, all the best to your team.
All right, thank you.
Thank you for your presentation. Yeah.
Thank you so much, Richard, for that informative and engaging presentation. Moving forward with our next presenter, I'd like to call upon Alina Miniteva to present her paper on studying C# application development through the creation of virtual reality projects. You may present your paper and share your screen.
And then building on that introduction, it's clear that VR and AR technologies are no longer niche. They are revolutionizing human-machine interaction across diverse sectors. These immersive technologies provide intuitive interfaces crucial for fields like industry, medicine, and education. They are indispensable for training, simulation, and modeling complex processes where traditional methods fall short. We've established a dedicated VR laboratory to leverage this shift. Focusing on C# development is as the core technical competency. This strategic move allows us to integrate C# programming, Unity physics, and immersive hardware to create the next generation of human-machine interface. Next, we'll delve into the specific infrastructure that supports this ambitious educational endeavor. Our VR laboratory is equipped with advanced hardware and specialized workstation essential for professional VR project creation. We utilized 7 HC Vive Pro VR handsets offering high resolution and precise motion tracking capabilities. Our workstation feature high-performance GPUs and ample RAM optimized for demanding Unity operation. The software stack and standardized on Unity 2022.3 LTS, OpenXR, and XR interaction toolkits, ensuring cross-platform compatibility. This environment is meticulously designed to foster both educational excellence and cutting-edge scientific research. This robust setup enables the integrated methodology we'll discuss next, combining C# theory with practical VR implementation. Let's now turn to the core of our educational approach in integrated methodology that combines C# theory with practical VR implementation. This balanced approach is crucial for enhancing learning outcomes, merging object-oriented programming principles with physics engine application. The theoretical component grounds students in C# OOP fundamentals and the core principles of the Unity physics engine. The practical component involves progressive laboratory assignments and culminates in student-led projects. Students advance from basic setup and camera configuration to complex interactive elements and via user interface. This progressive learning path directly contributes to the significant boost in student engagement and motivation. We'll explore on the next slide. Our project-based learning approach centered on VR development has proven highly effective. A survey revealed that 84% of students found VR-based learning more engaging than traditional instructional methods. Furthermore, 79% reported increased motivation to study C# and Unity in greater depth, indicating a profound impact on the academic drive. This hands-on experience also boosted confidence, with 68% of participants feeling more assured in their development skills. These results underscore how project learning effectively bridges the gap between theory and practice, preparing students for real-world challenge. However, this innovative approach also presents unique technical barriers, which we'll address next. While project-based learning significantly boosts engagement, we must acknowledge the technical hurdles students face. Our research indicates that overcoming these barriers is crucial for successful VR education. A significant portion of students, 42%, struggled with the intricacies of 3D graphics and game engines, highlighting a substantial knowledge gap. Furthermore, 26% encountered difficulties with hardware configuration, underscoring the need for robust technical support. Next, we'll explore a specific project that exemplifies how this challenge can be addressed through practical application. Building on the need for practical application, our VR public speaking training offers a compelling solution for skill development. This project enhances oratory with skills for realistic simulation, providing an immersive environment for use to practice in recreates realistic presentation conditions with virtual audiences, allowing us to manage stage fright effectively. The system records critical speech metrics like duration and volume, providing valuable feedback for improvement. This project developed with Unity 2022.3 LTS and OpenXR demonstrates how we can create effective, accessible training tools. Now let's examine another project that tackles complex operational training. Expanding on the theme of the immersive training, the Lunar Research Station simulator models complex extraterrestrial operations. The similar includes scenarios for station maintenance, sample collection, and extravehicular activities, offering invaluable educational experiences. This project highlights VR's potential for advanced operational training. And now I'm going to play video now. Next, we'll shift our focus to a project that explores interactive retail processes. This project immerses us in a realistically modular retail space, allowing them to experience and interact with products. The system also includes a virtual shopping basket and fixed location checkout interface, showcasing MVP development for commercial VR applications. This project illustrates the versatility of VR in simulating real-world scenarios. Now let's look at projects focused on immersive puzzle solving. This project highlights the potential of VR to transform learning through interactive problem solving, and it sets the stage for our next application, which focuses on therapeutic use of VR. And this simulator utilizes controlled exposure to related stimuli to help users manage and overcome phobias. The methodology involves a gradual ascent in a virtual urban environment with real-time head tracking, providing precise feedback. This project demonstrates how VR can provide a structured and secure setting for therapeutic adaptation to heights, leading us to our concluding thoughts on the broader impact on VR in education. In conclusion, our VR integration and university establish a robust foundation for the future of engineering education. You've seen that this project-based approach significantly boosts students' motivation and enhances practical C# programming competencies. The student development themselves are not just exercises, they serve as a foundation for new scientific publication and experimental studies and in VR and AR technologies. Looking ahead, we plan to expect VR application into complex engineering tasks, industrial modeling, and medical simulations. We also intend to conduct further studies on how VR influence cognitive processes, information acquisition rates, and long-term engagement. So thank you for listening.
Excellent work, Alina. Thank you so much for your presentation.
Do you have any questions for her?
No question. The work is, she explained it so well. There are no questions left, actually.
Thank you, Alina, for your meaningful contribution in this session. It was a pleasure having you here. Next, I would like to call upon our next presenter, Fernando Latorre, to present his paper on Unified Health Index as a service for cross-jurisdiction emergency care. You may present your paper by sharing your screen.
Yes, good morning.
Good
I will
morning.
share the screen. Okay. My name is Fernando Latorre. I'm Chief Technology Officer at Connect Health and Vice President of UNIT Foundation. And today I will present the Unified Health Index as a service for cross-jurisdiction emergency care. The core idea is simple: enable fast emergency discovery and controlled access without centralizing clinical records. This work is part of Global Data Care, a European data space for human and animal health promoted by Accuro Technology. Okay, and let me check. Okay. This is what emergency identity has looked like for decades: a physical card with personal static data like name, blood type, allergies, emergency contacts, and medication. The limitations are clear: no dynamic updates, no section level access control, and privacy concerns. If something changes, like a new medication or allergy, the card is immediately updated, and there is no way to enforce who can see which part. Now, the card stores an identity pointer, not personal and medical data. The decentralized identifier is resolvable over standard web infrastructure and returns a decentralized identity document or the document. That the document contains public signature keys for verification, service endpoints showing where to recover or notify information, and also digital identities of legal representatives. So instead of printing data, you print a QR code and a decentralized identifier. And you can also display that identifier in a SOS screen on mobile devices. The Unified Health Index is a new service on top of current local health data providers using the health interoperability standards. Providers notify the Unified Index of new record links under the individual's authorization. The individual does not need to manually retrieve and index records through a web or mobile app. The key idea is data is linked but not moved. And this is why the button works. Consent leads to an index plus policies, and that leads to secure accessibility. In this slide, we explain the user experience with a simple three-step flow. Let me check. Okay. Oh, sorry. I think I was wrong with the slide. Okay. Sorry, I was lost. Let me check. Okay. This is the 7. Okay. The Unified Health Index. Okay, sorry for this gap. Sorry. The Unified Health Index is this new service. The providers notify when the records are new, and in this way, links are updated. The important thing I missed, sorry, is this is in inclusive service because people doesn't need a mobile application because only is needed to sign the consent in an organization that is a member of the data space. So in this way, people can start having the service ready, and in this way, using any identifier linked to the index, the doctors and practitioners can have access to the data that is linked in the index. Okay. And now. This is the three-step flow. The organization connects to the data space, the patient grants permissions, and the request is solved instantly. The book analogy is applying what matters. A person's history is like a large book, but each chapter is stored in a different library. Today, you travel with each library to request permission and compose your own index, but the unified index doesn't copy the results from clinics or from hospitals. It receives data that store links and tells you which library and which shelf each chapter is on. For example, one chapter can be labs for a clinic or diagnostic records in other hospital, or vital signs from a wearable device. And in the emergency access, the hardest question is how we handle emergency escalation without a silent override. The rule is always must be auditable. The Tier 1 is pre-authorizes emergency access when role and jurisdiction match, using a scope or fine-grained access token and retrieving specific summary sections, fully policy-driven. Tier 2 is curated emergency dataset defined by the individuals, such as contacts, allergies, implants, for example, a pacemaker, and similar critical items with quick access and minimal necessary scope for doctors, nurses, and paramedics. And Tier 3 is very class escalation under legal emergency doctrine, verified doctor, signed justification, time limited scope, full audit trail, and notification after the event. One important thing is that clinical custodians remains independent and must validate scoped tokens before disclosing records. In the data anonymization, in this slide, we define digital twins as metadata of an unknown individual over time, a snapshot of at a point in time, evolution over time, and a forecast of possible pathways. What is anonymized and when? Metadata, when certifying a document, and then the digital twin is updated by the index provider if consent is not revoked. The metadata are datasets that do not allow identification, like sex, year of birth, jurisdiction, where the data is created, date of creation, and clinical or product code. For example, you will be able to study how certain tests or treatments are used across jurisdiction without knowing who the person is. And anonymization alone is not enough. Governance and verifiable trust are equally essential. So this is the trust architecture in the data space. At the top, the governance entity authorizes intermediate certification entities and oversees compliance aspects, including software and algorithm ethics. Trusted certification entities verify organizations joining the data space and issue signed verifiable credentials that prove their real-world identity. Once an organization receives its signed credential, infrastructure nodes operators provide hosting and technical services, allowing the organization to deploy and operate its connector within the data space. Each verified organization then issues verified credentials to its employees, binding their role and email to cryptographic keys, so every action is attributable to a specific professional. These employees can perform identity evidence checks for end users such as patients or legal representatives and register that evidence using the organization's connector. Finally, the end user signs consent to activate the unified index and registers permissions, linked records, and related persons. This layer chain ensures that consent, access requests, and data interactions are traceable to verified organizations and verified roles. This is the data flow answering scheme. The diagram summarizes how the system works in practice and is designed around user sovereignty. At the center is the individual. They activate the unified index, register emergency contacts and identifiers, and grant organized permissions to link data. Data providers give their own systems and expose a standardized interface to share documents when authorized. The index service, shown here as a demonstration center, manages unified consents and unified health index. It stores permissions and authorizes links, not clinical records. Authorized data consumers, such as clinicians or emergency professionals, access the information using their usual clinical system that supports standardized health data formats. In addition, when consent allows secondary use for research, anonymized and non-linkable metadata are derived from the unified index, such as sex, years of birth, jurisdiction, creation date, and clinical or product code. And in this way, participant organizations can use this anonymized digital twin history to build longitudinal models and analyze real-world evolution over time without identifying any individual. The result is a controller sharing and for continuity of care and research without centralizing records. And finally, in this way, emergency data access must be cross-border, fast, and auditable. So the Unified Health Identity enables discovery of where the Unified Health Index resides. The Unified Health Index enables controlled access to authorized data links. Clinical data remains with original custodians, and access is fine-grained and policy-driven for continuity of care, and supports emergency escalation with auditable every class. Thank you very much for your attention, and I will be happy to answer your questions.
Hi, Fernando. This is good. This is something up my alley. I was working with a lot of systems using blockchain. But the question that comes to my mind is how do we ensure that right to be forgotten for a customer or for a person whose data is here in accordance with HIPAA compliance or with GDPR is maintained?
Mhm. Yeah, is the index is the service that lists the information. So if the patient wants to change to other provider, is transferring the index to the other provider and deleting the index in the current provider. So there is no problem with the blockchain because the blockchain is used only to store the hash, the digital fingerprint of the permissions and of the digital keys, the public keys that the employees or the users or the organizations are using in the inside data space to control when a key, a public key, this is the digital identity, when it's revoked, when it's protected. So this is how the blockchain is used. It's basically for traceability of the public keys and for the to have the digital fingerprint of the documents and the permissions that are created.
The hash algorithm must be very strong here, actually. So there can be questions and then be something that we can break. There will be necessary that
Sorry, I have some problems with the audio.
there are hashes that there are a lot of ways we can try to recover the hash. So your hash algorithm must be explicitly strong to ensure that the privacy is maintained still.
I lost the audio. Sorry, I don't know if you can hear me
But your
properly.
voice is cracking a lot.
Okay, no worries. Thank you so much. It was something I'll have to connect directly to him to understand how his system works. I'll send you a LinkedIn request.
Perfect. Thank you.
Thank you.
Thank you so much, Fernando, for that enriching presentation.
You're welcome.
Yes. Now, I would like to conclude this session by sincerely thanking our authors for their excellent presentations and valuable contributions to this session, and all of our participants for being a part of this international conference. I hope this session was informative and enriching for everyone. All the presenters will receive their digital certificates via email within 2 working days. The publication will be live within 7 to 8 months. Kindly cooperate with the ICICT 2026 team. On behalf of the entire team, thank you for your continued support through the 11th edition and all the previous editions. We look forward to welcoming you again for the 12th edition in 2027. Now, as a token of appreciation for our session chair, I'd like to display this certificate on behalf of Team ICICT 2026 and Global Knowledge Research Foundation and partners. I would like to invite Dr. Sachin Gupta to kindly deliver some closing remarks.
I enjoyed the sessions immensely, and some of them were so resonating that I would have to update my research work again. Thank you for the presentations, everyone. You did a very good job, and we look forward to continuously tracking your research, how it progresses. Thank you.
Thank you so much, sir. Now, I would kindly request everyone to switch on their cameras for a quick snapshot of the virtual conference as valuable memories that we can display on our conference website. Everybody, please switch on the cameras. Give me a nice smile. Thank you, everyone. It was wonderful having you all here. Very honored to host this session. Take care. Stay safe. Bye-bye.
Thank you.
Bye.
Thank you.
Thank you so much.